Have you ever stopped to think about like how often you actually use the search function?
Mhm.
I mean, whether it's finding a file on your computer or, that one specific bit of information and a really long article, even just like using your phone to find the closest coffee shop.
Yeah.
I mean, searching is something we do all the time. And it's all powered by these things called algorithms,
Right.
which are just, sets of rules or instructions that tell computers how to find the stuff we need, right?
Yeah, exactly.
So today we're gonna take a deep dive into one of the most fundamental algorithms out there, particularly when it comes to dealing with a ton of data,
Okay.
and that is binary search.
Interesting.
And our mission today is pretty straightforward, right?
Mhm.
We just want to understand, like, how does binary search work, and when is it like the best tool for the job, right?
Right.
So to help us out with this, we've gathered some pretty interesting material, including a transcript from a Code Curious YouTube video
Cool.
featuring Catherine Medina Develers, who knows a lot about this stuff. So to kind of kick things off, it's interesting to think that something as basic as searching actually requires a very specific method when it comes to computers, right?
Yeah.
I mean, think about it like this, right? If you had like a whole bunch of unsorted notes
Yeah.
and you were looking for one specific piece of information, you'd probably just go through them one by one, right? Until you find it.
Mhm.
That's essentially what's called a sequential search.
Yeah.
It's
Yep.
like imagine a line of numbered marbles,
Okay.
and you're trying to find the one with number 31 on it.
Right.
You would just start at one end and check each marble one by one until you found it.
Yeah,
right?
absolutely.
So that's sequential.
Makes sense.
But what if there was like a smarter way? Like a much faster way to find what you need,
Yeah.
especially when like things are organized.
Right.
What if there's a technique that can really like speed things up significantly?
Uh-huh.
That's where binary search comes in.
Okay, yeah. I'm interested.
So let's unpack this a little bit. Right?
Okay.
So the first thing to understand about binary search is that it's got this really important requirement. The data has to be sorted.
Right.
It can't just be random.
Uh-huh.
And Catherine Medina Develers, she makes this really clear in the transcript, right? She says that it could be sorted in like ascending order,
Okay.
like numbers getting bigger, 1, 2, 3, 4, 5,
Yeah.
or descending order, like going from Z to A
Yeah.
in a list of names, right?
Right.
So that's really important.
Yeah, it makes sense, right? If everything was just jumbled up, how would you even begin to search through it efficiently?
Exactly. There'd be no system to it.
Yeah.
So with that sorted data in front of you, binary search uses what's often called a divide and conquer strategy.
Okay.
So what does that actually look like in practice?
Well, here's where it gets really interesting, right? So the algorithm itself, what it does is it repeatedly divides the search area in half. But here's the thing, right? It's really important to keep in mind, and the transcript really emphasizes this, computers can't see in the way that we do.
Right.
They're not visually scanning a list.
Uh-huh.
What they do is they operate using the indexing of a list.
Right.
That's the position of each item, right?
Okay, so it's all about like the numerical location of things in that list.
Exactly.
So how does the computer actually pinpoint that middle spot?
So it's a pretty straightforward calculation for the computer, right?
Okay.
What it does is it takes the index of the first item, that's the lowest index,
Uh-huh.
and then the index of the last item, the highest index, adds them together and divides by 2.
Okay.
That gives you the middle index
Gotcha.
of the current part of the data that it's looking at,
Okay.
right? And then the computer goes to that middle position and checks what's there.
Okay, so it finds the middle item, and then what? What happens next?
Well, this is the really clever part, right?
Mm-hmm.
So it compares the item at that middle index with what you're actually searching for.
Uh-huh.
Now, if what you want is smaller than the middle item,
Mm.
then you know it has to be in the left half of the current range,
Right.
because the data is sorted,
Yeah.
right? If it's larger, then it has to be in the right half.
Right.
And if by some amazing chance the middle item is exactly what you're looking for, then you're done.
Boom. Search is over.
Search is over.
That's it.
Right.
Yeah, that's super efficient.
It is.
Just by looking at that middle point, you've already eliminated like half of the data, right?
That's right.
And I think the transcript gives a really good example for that.
Yeah.
Let's say you're looking for the number 27 in the sorted list. 7, 10, 14, 27, 31, 35, 42.
Okay.
With binary search, the computer's going to calculate that middle index, which in this case like points directly at 27 on the first try.
Exactly. First try and you're done.
It's right there.
Yeah.
Now compare that to the sequential search example, right?
Yeah.
That's also in the transcript. Where if you were looking for, let's say, 31,
Okay.
you might have to look at like a bunch of numbers before you actually find it.
Right.
So by taking advantage of that sorted data,
Yeah.
binary search really cuts down on the number of times you need to check.
It does. It's a huge time saver, especially when you're dealing with larger data sets.
Absolutely, yeah. So the transcript also mentions that it might be helpful to visualize this whole process as like a binary search tree.
Yes.
Now, keep in mind, the computer isn't actually building a tree in its memory,
No.
but it's just a helpful way for us to kind of like picture what's happening, right?
It is. It is.
Can you kind of walk us through that?
Yeah, so picture the root of the tree as the middle of your entire sorted list, right?
Mm-hmm.
So the left branch from that root represents the middle of the low half of the list,
Okay.
and then the right branch represents the middle of the upper half.
Right.
So each level you go down in this like imaginary tree represents another halving of the search space.
Right.
The transcript uses that same example again, you know?
Yeah.
27 is the root, 14 to the left, 35 to the right, and you can see how quickly you can narrow things down.
Yeah.
In the worst case scenario, in that small example, it only takes 3 lookups, right?
Right.
But it's really important for you to remember that this tree analogy is just for us.
Yes, for our brains,
It's for our brains, yeah.
the algorithm itself is working directly on that sorted array using those indexes.
Yeah, that's the real magic happening behind the scenes.
Right. So it's like each step gets you dramatically closer to what you're looking for.
That's right.
Now, to make this even more relatable, I thought the transcript brings up a really interesting example.
Oh, yeah.
Do you remember that clocking miracle from The Price is Right?
Oh, of course. Yeah, classic.
So the contestant there, right, when she's trying to guess the price of the item, she's essentially using a form of binary search
Yeah, without even knowing it.
without even realizing it.
Yeah.
So after each guess, she's getting that feedback, right?
Yeah.
Higher or lower. And that allows her to rule out a huge chunk of the possible prices.
Exactly.
She wasn't just randomly guessing numbers.
Yeah.
She was strategically narrowing it down. Right?
Absolutely. It was a brilliant strategy.
And it really mirrors that whole idea of divide and conquer, right?
It does.
In a way that's like super easy to understand.
Yeah, a perfect real world analogy.
And the cool thing is, she actually won $1,000 by landing right on $749.
What a moment. Yeah.
It's just a cool example of how this approach actually works in everyday life,
Yeah.
even if we don't think of it as like a formal algorithm.
Yeah.
So now I think a lot of people might be thinking, okay, this sounds faster, but like how much faster?
Right. Yeah.
You know, and the transcript really gets into this whole idea of efficiency,
Hmm.
particularly in like the worst case scenario.
Okay.
Like if you have this massive set of sorted data,
Yeah.
what's the maximum number of checks you might need to do to find what you're looking for?
That's the question.
Yeah, and I was pretty blown away by the numbers here.
Yeah.
So for a list of 600 sorted items, the maximum number of lookups with binary search is only about 10.
That's right.
That's pretty impressive.
It is. It is.
So how do we even like figure that out?
Okay, so you can roughly estimate this by just repeatedly dividing the total number of items, in this case 600, by 2. And you keep doing that until you get down to 1,
Okay.
right? The number of times you have to do that division is basically the worst case number of comparisons.
Yeah.
And this is what we call logarithmic, right?
Right.
Which means that binary search is like really good at handling these huge amounts of data.
Like super efficient.
Super efficient, exactly.
Yeah.
And this whole concept of logarithmic time complexity, this has revolutionized how we retrieve data. And it really underpins so many of the technologies that we use today
Right.
that rely on quick searches in these massive databases.
Right, yeah. So let's bring it back to that comparison with sequential search.
Okay.
We've got another example here in the transcript.
Uh-huh.
So this time we're searching for 54 in the list, 10, 22, 32, 48, 54, and 60.
Okay.
So with sequential search, you'd have to check each number one by one, right?
Right.
Until you hit 54.
Yeah.
And that's going to take 6 comparisons.
6 comparisons, yeah.
But with binary search, walk us through what happens.
Okay, so binary search, right? It's going to first look at that middle item, which is 32,
Mm-hmm.
since 54 is greater than 32.
Yeah.
It immediately eliminates the entire left half of the list.
Right.
It doesn't even have to look there.
Yeah, it's gone.
It's gone. It's just like, nope, not there.
Exactly.
Right.
And then it looks at the middle of the remaining right half,
Uh-huh.
finds 54, and boom, it's done in just 2 comparisons,
Wow.
right? Even in the worst case scenario for this small list, binary search would only take 3 comparisons.
Yeah, that's a massive difference.
It's a huge improvement.
Now, I think a lot of people might think that binary search is only for numbers.
Yeah, that's a common misconception. But the transcript clarifies that it's much more versatile than that.
Oh, absolutely.
So could you kind of expand on that?
Yeah, so binary search can be used for any type of data that can be ordered.
Okay.
Think about like a dictionary, right? A
Mhm.
dictionary is alphabetized,
Right.
and you can find a word super quickly by just flipping to the middle,
Yeah.
seeing if your word comes before or after that middle word, and then narrowing down your search from there.
Right.
And the transcript actually gives an example of this, searching for the word mango in this alphabetically sorted list. Apple, banana, kiwi, mango, orange.
Right. Right.
And this applies to so many things, like how you might search through a sorted list of documents, contacts.
Yeah.
It's a very common pattern.
So in that example, kiwi would be the middle word.
Exactly. Kiwi is in the middle.
And since mango comes after kiwi alphabetically,
Right.
the search moves to the right half of that list.
That's right.
And boom, mango is found on the next look.
Next look. Done.
Awesome.
Yeah.
And it doesn't even have to be in ascending order, right?
Yeah, that's another key point.
Like you could have a list of words that are sorted in reverse alphabetical order,
Yep.
and binary search would still work as long as that ordering is consistent.
Right. As long as the algorithm knows what to expect.
Yeah, exactly.
Yeah.
So just to kind of like recap some of the key takeaways from the transcript here,
Sure.
what would you say are the most important points?
Okay, so first and foremost, the data absolutely must be sorted.
Okay.
It can be either ascending or descending, but it has to be sorted.
Gotcha.
Secondly, it's all about that divide and conquer strategy.
Right.
You're repeatedly having that search space.
Uh-huh.
Thirdly, and this is really important to remember, it's not just for numbers.
Right.
It works for any ordered data,
Mhm.
like those alphabetical lists of words.
Yeah, yeah.
And finally, in most cases, binary search is going to be way more efficient than just going through each item one by one.
Right, which is what that sequential search does.
Exactly.
And the transcript also has some really cool practice questions in there.
Yeah, they were great.
I thought those were really helpful just to
Yeah.
kind of like solidify these concepts.
Absolutely.
So they covered things like how to find the middle index,
Mm-hmm.
the difference in those comparisons between binary and sequential.
Yeah.
And again, how binary search applies to ordered words.
Right.
I think one question highlighted that if 16 is the middle number in a list,
Right.
you calculate that middle position by adding the first and last index and
Yeah.
then dividing by 2.
Exactly. That's how you find the middle.
Yeah. And then another one showed that finding the value 22 might be at index 5 in a given sorted list.
Uh-huh.
And that was a good illustration.
Yeah.
And importantly, right, the practice questions really emphasize that finding a specific element, like let's say 31,
Yeah.
takes way fewer comparisons with binary search
Oh, absolutely.
compared to just going through each element sequentially.
Yeah, you save so much time and effort.
So much time.
Yeah.
And it's worth repeating again, right? Binary search works great on alphabetically or reverse alphabetically ordered words,
Mm-hmm.
as well as those numerically ascending lists.
That's right. Any consistently ordered data.
Right, and then one of the last practice questions pointed out that for a list of 200 sorted numbers,
Okay.
the worst case scenario for finding a specific number using binary search is only about 8 lookups,
That's it. Just 8.
which is just mind-blowing.
It is. It really highlights the power of this algorithm, especially when you're working with these large data sets.
Yeah, absolutely. So to kind of like wrap things up here,
Okay.
what would you say are like the final takeaways that Catherine Devlers wanted to leave us with in the transcript?
So the core message, right, is that binary search is this fundamental algorithm.
Uh-huh.
It operates on this principle of conquer and divide.
Right.
It absolutely requires the list to be sorted beforehand.
Yeah. You have to emphasize that enough.
Cannot emphasize that enough.
Yep.
And it is very often the most efficient way to search for a specific piece of information.
Right. Within that sorted data.
Within that sorted data.
Awesome. So there you have it. Binary search. A seemingly simple, but like incredibly powerful algorithm
It really is.
that powers so much of the searching that we do every single day.
You don't even realize it's happening half the time.
Yeah, it's happening behind the scenes.
In the background.
So I encourage everyone, next time you find that file in like milliseconds, just think about binary search for a second.
Yeah. Appreciate the algorithms working for you.
Exactly. So I think this raises an interesting question, right? That
Yeah.
Now that we understand how a computer can pinpoint one specific piece of information so quickly in like a huge ordered collection,
Yeah.
what other problems in our own lives or in our work
Right.
could benefit from this kind of approach?
It's a great question. And you know what? It really boils down to being able to structure or sort the relevant information, right? If you can find a way to organize the data in a meaningful way, then you can apply these powerful algorithms.
It's like finding that underlying structure.
Exactly. And that's a challenge in itself, but it opens up a world of possibilities.
And it makes you really wonder about all the other cool algorithms
Yeah.
that are out there.
The unsung heroes of the digital world.
Exactly. Silently shaping our digital world.
Behind the scenes, making things work.
So we hope this deep dive has given you a new appreciation for the efficiency and the ingenuity
Yeah,
behind something as fundamental as searching.
absolutely.
And until next time, keep exploring.